Well, thank you for joining me today as we look at our homework from the calculus and cardinality proofs. All right, so for our first example, what we want to do is we're going to show the limit as x goes to -1 of 4x plus 6 is equal to 2. So just like with our other limit proofs, we have to say let epsilon greater than 0 be given. We're going to end up choosing a delta so that we can show that f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus c is less than delta. So I'm going to start with here, and I'm going to say f of x is 4x plus 6, and I have to subtract L, so minus 2. And then I'm going to simplify that, so eventually I'll get out less than delta. So if I do that, I get 4x plus 4. I can factor out the 4, and I get the absolute value of 4 times x plus 1. Now, the absolute value of a times b is the absolute value of a times the absolute value of b. So this is 4 times the absolute value of x plus 1. And notice that the absolute value of x plus 1 is x minus -1. So what I get, and the reason why I'm writing that is because now I have x minus c, which is -1. So I know that this is less than delta, so this is less than 4 delta. Well, what should I let delta be if I want 4 delta to be equal to epsilon? Well, I should let delta be epsilon over 4. So therefore, 4 delta is equal to epsilon. And I get f of x minus L is less than epsilon whenever x minus c is less than delta. Hence, the limit as x goes to -1 of 4x plus 6 is indeed equal to 2. For our next example, we want to show that the limit as x goes to 8 of 2x minus 7 is equal to 9. So again, we're going to let epsilon be greater than 0. We're going to choose a delta, and we have to show that f of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta. So if I just start off, f of x here is going to be 2x minus 7. Then minus 9 is my limit. So f of x minus L, which is going to be equal to 2x minus 16, which is 2 times x minus 8, which is 2 times the absolute value of x minus 8. But we know that x minus 8 is less than delta, so this is less than 2 delta. So if we just let delta equal epsilon over 2, 2 epsilon over 2 is just epsilon. So f of x minus L is less than epsilon whenever x minus c is less than delta. All right, now what we want to show is that the limit as x goes to 0 of the absolute value of x over x does not exist. So we're going to work by way of contradiction and assume that it does exist. Well, if it does exist, then for any epsilon greater than 0, there exists a delta such that for x minus, or absolute value of x less than delta, f of x minus L is less than epsilon. Well, what that means is that, note that if the limit as x goes to 0 of absolute value of x over x is equal to some L, then what that means is that the absolute value of x over x minus L is less than epsilon for any epsilon when 0 is less than the absolute value of x is less than delta. So we get that that has to be true. However, what we want to do is we want to show that that can't be true. All right, well, how are we going to do that? Is, well, note if x is greater than 0, then even if x is less than delta, so if 0 is less than x is less than any delta, then what I get is the absolute value of x over x is equal to 1. If negative delta is less than x is less than 0, then what we get is still the absolute value of x is less than delta. We have that the absolute value of x over x is equal to -1. So we take absolute value of x for positive is just x over x, we get 1. For negative, it's negative x over x is just -1. So as x goes to 0, if x is bigger than 0 but still less than delta, we get 1. If x is less than 0 but still less than delta in absolute value, we get out -1. And it doesn't matter what delta, so this is working for all delta. Therefore, what this is saying is that Well, negative 1 minus L is less than epsilon, and 1 minus L is less than epsilon for any epsilon. So what we can get is, let's just pick, say, epsilon 1/2 is, this is telling us that, well, we're going to get that 1 minus 1/2. Our 1 minus L is less than 1/2, and negative 1 minus L is less than 1/2. All right, well, what does that mean? Well, if I use this one, this tells me that negative 1/2 is less than 1 minus L is less than 1/2. So if I subtract 1, I get that negative 3/2 is less than negative L is less than negative 1/2. And so if I multiply by negative 1, I get 3/2 is greater than L is greater than 1/2. So I have that. On the other hand, I have that negative 1/2 is less than negative 1 minus L is less than 1/2. So if I add 1, I get 1/2 is less than negative L is less than 3/2. And if I multiply by negative 1, I get negative 1/2 is greater than L is greater than negative 3/2. Well, if I combine these together, I get that 1/2 is less than L is less than 1/2. So 1/2 is less than L is less than negative 1/2. What does that mean? Well, that means that if the limit exists, then 1/2 has to be less than negative 1/2. Since that is not true, it is clearly a contradiction. So we have found our contradiction, therefore the limit cannot exist. All right, so what we want to do is we want to find that the cardinality of R is equal to the cardinality of the interval from square root of 2 to infinity. What does that mean? Well, that means that I have to find a bijective mapping from R to the square root of 2 to infinity. So I want to find some alpha that maps R to the interval root 2 to infinity. Now I'm just going to pictorially do this to figure out what that should look like. Is I'm going to say here's the square root of 2. So I have to find a one-to-one mapping which is onto everything above that point. So what might that look like is, well, I would want to get arbitrarily close to here, so I'm going to make it a horizontal asymptote. And I'm going to increase the whole time so that I stay one-to-one. And I'm going to go off towards infinity. So there's my mapping. There is a one-to-one onto mapping from the set of real numbers to the square root of 2 to infinity. Notice it's one-to-one because it passes the horizontal line test. It's onto because I can get out any point in there. Now, if I wanted to be more precise, I could actually give this a function and say, well, what does that look like? Well, to me, that looks like an exponential just moved up. So I'm going to say, let alpha of x be equal to e to the x plus the square root of 2. And then you can go ahead and prove that that's one-to-one and onto. So let's go ahead and do that for this one. All right, to show that this is onto, what I have to do is I have to let y be in the interval of the square root of 2 to infinity. And I have to find something that gets mapped here. So the way I would do that is I would just say y is equal to e to the x plus the square root of 2. And I have to say, okay, well, what would x be in terms of y? So I get y minus the square root of 2 is equal to e to the x. If I wanted to solve for x, I should get natural log of y minus the square root of 2 is equal to x. And so what I've done is I've found the x that would get mapped to y. So now, as I said, this is side work. So as part of my proof, I would say, well, let x equal natural log of y minus the square root of 2. Note, x is a real number. So we want to show that that's in the domain, and it's a real number because, well, if I take something bigger than the square root of 2, minus square root of 2, I'm still positive. I can take the natural log of a positive number, so this is well defined, so it is a real number. Now, if we take alpha of natural log of y minus the square root of 2, we get e to the natural log of y minus the square root of 2 plus the square root of 2, which is y minus the square root of 2 plus the square root of 2 is just y. Hence, we found an x in the domain, which gets mapped to any y in the range, or the codomain, Therefore, this is indeed an onto mapping. All right, to show that this is one-to-one, what I'm going to do is assume that alpha of A is equal to alpha of B, and I want to show A is equal to B. Well, what does this mean? This means that e to the A plus the square root of 2 is equal to e to the B plus the square root of 2. So I can subtract square root of 2, and I get e to the A is e to the B. I can natural log of both sides, and I get A is equal to B. Hence, if alpha of A is equal to alpha of B, A is equal to B. So it is indeed a one-to-one mapping. So what we found was that we were able to find a one-to-one onto mapping from the set of real numbers to the interval, the square root of 2 to infinity. Therefore, those things have the same cardinality, or they consist of exactly the same number of elements. All right, now what we want to do is show that the set of real numbers and cardinality is the same as the set of real numbers between 0 and 1. And so what I have to do is find a one-to-one onto mapping from the set of real numbers. So let's say alpha from R to 0, 1. And so I'm going to start off the same way I did last time, is pictorially. Here's 1, here's 0. I just need to draw a picture, which is one-to-one and onto. Well, I want to get close to 0 but never equal to it, and close to 1 but never equal to it. So I'm going to do the same thing I did last time, is make a horizontal asymptote. I'm going to increase so that I stay 1-to-1, and then I'm going to have another horizontal asymptote at 1. So I'm going to get arbitrarily close to 0, arbitrarily close to 1. I'm going to hit everything in between. So this will indeed be a one-to-one onto mapping from the set of real numbers to the interval 0 to 1. Now, if you wanted to, you could figure out, okay, what is a function that actually looks like that? But we did that last time, so I'm going to just refer you back to the last problem to say, how would you do this in general? Is you'd have to find some function. But at least for our purposes, we found a one-to-one onto mapping because we gave it graphically, so therefore we've shown that these have to have the same number of elements. Let's show that the set of irrational numbers is not countably infinite, or that is, it's uncountably infinite. Well, the way we're going to do this is actually proof by contradiction. So assume that R not Q is countably infinite. Notice that what we get then is that, well, if I take the union of R not Q with Q, I just get out the set of real numbers. But what we proved in class was that the set of real numbers was countably infinite. So if this is countably infinite, that would mean that, well, the set of real numbers would be the union of two countably infinite sets, and therefore, as we proved in class, would be countably infinite. However, we also proved that R was not countably infinite. Therefore, we can't have that the irrationals are countably infinite, because if they were, the reals would have to be countably infinite, and that's not the case. So notice that, okay, these are uncountably infinite, and so what that's really telling me is that there's many more of these than these. That is, the cardinality of R naught Q is strictly bigger than the cardinality of Q, because the cardinality of Q was countably infinite. So, as a side note here, notice that we spent a lot of time talking about rational, irrational numbers, but most of the numbers we've dealt with have been rational, and there's only been an odd 1 or 2 irrational numbers that we're able to come up with. What we've just proven is that there are actually vastly more irrational numbers than rational numbers. And so if we were to pick an arbitrary real number, it is extremely likely that it would be an irrational number, because there are just so many more irrationals than irrationals, which is really counterintuitive from what we built up so far, because we spent so much time working with rational numbers.